Hello students, today I am going to give a lecture on unit number 4 part 2 single phase transformer. Syllabus: Principle of working, construction and types, EMF equation, voltage and current ratios, losses, definition of regulation efficiency, determination of these by direct loading method, descriptive treatment of auto transformers. These are the contents of today's lecture: principle, construction, types of transformer, EMF equation of transformer, ideal transformer, transformation ratio, voltage, current and turns ratio. Now this is the use of transformer. This is the application of power plant. In the power plant, here the transformer used as a step-up transformer for raising the voltage and again for the transmission purpose, and at the distribution end there is a step-down transformer which lowers the voltage. So transformers are used whenever we required to change the voltage levels. Now what is a transformer? Transformer is a static device which transfers electrical energy from one circuit to other circuit without change in frequency. The two circuits are electrically isolated. They are connected by a medium of magnetic circuits. Now in this diagram, here is the winding of the coil which is connected to the AC supply, which is known as primary winding, and here is the winding which is connected to the load, is known as secondary winding. So both the windings are electrically isolated, but they are inductively coupled through a common magnetic circuit. Now working principle of transformer. The working principle of transformer is based on mutual induction, which states that when two coils are inductively coupled and if current in one coil is changed uniformly, then an EMF get induced in the another coil. Now here is the example. The coil which is having N1 number of turns is connected to AC supply, which is nothing but the primary winding. The winding which is having N2 number of turns is connected to the load, which is known as secondary winding. Now AC supply V1 is given to the primary winding. Alternating current I1 is flowing through the windings of the primary, and due to this alternating current, alternating flux is produced. Due to this flux, EMF get induced in the primary. That EMF induces E1, which is self-induced EMF. Now this alternating flux is taking the common magnetic path and it links with the secondary coil, due to which in the secondary coil EMF get induced, that is E2. So this is the working principle of transformer. Now this is symbolical representation of transformer. This is primary, this is secondary, and this vertical line shows the magnetic code. Now can we give DC supply to the transformer? No, we can't give DC supply to the transformer, because the working principle of transformer is based on mutual induction. Mutual induction means there is a change in the current and change in the flux is required. In case of DC, the current is constant, so there is no change in the flux. Again, in case of DC, the reactance is 0 and the winding resistance is very small, so very high current flows through the windings, which may damage the transformer. Hence, transformer can't work on the DC supply. Next is the construction. Transformer has two parts, core and winding. So in case of core is mainly used material. The material which is used for the core is high grade silicon steel. Due to this material, hysteresis loss can be reduced. Now core has two parts. Horizontal part is known as yoke and vertical part is known as limb. So the function of the yoke is it gives magnetic path to the flux. It gives low reluctance magnetic path to the flux, and limb carries the windings which carries current. Now core of the transformer is laminated and each lamination is insulated from each other by varnish. Due to this laminated structure, eddy current losses can be reduced. Laminations are provided in different shapes T, U, L, I, E with the thickness varies from 0.3 mm to 0.5 mm. Now these are some the laminations of different shapes. Commonly used shapes are I type and L type. These are some laminations which are used for shell type and core type of transformers. Now the second part of the transformer is winding. Winding is made up of copper. So area of the limb depends on the type of the coil, either circular or rectangular, because the windings are on the vertical limbs. Coils are wound on same limb and are insulated from each other. The core has to provide low reluctance path to the flux and windings needs to carry the current. Now these are the two types of transformers. One is known as core type of transformer and another is known as shell type of transformer. So in the core type of transformer, the windings are on both the limbs, and in the shell type of transformer, the winding is on the central limb. Now the winding arrangements for core type and shell type of transformers are different. So depending upon that, there are two types of windings. One is known as cylindrical concentric type of winding. So the cylindrical concentric type of windings are used in core type of transformer. These are wound in helical layers. The different layers are insulated from each other by paper, cloth or mica. Low voltage winding is placed near the core and high voltage is placed after it. Means the windings are divided into number of turns, and then the low voltage winding is placed near to the core and high voltage is placed over it, due to which the insulation problem can be reduced. Now the second type of winding is known as sandwich type of winding. The sandwich type of winding is used for shell type of transformer. Each high voltage portion lies between the two low voltage portion, sandwiching the high voltage portion. Due to such a subdivisions, leakage flux gets reduced. So in the diagram, if you see, the two low voltage windings are at the ends and high voltage winding is sandwiching between the low voltage winding. So due to this type of arrangements, the leakage flux can be reduced. Now the comparison of core type and shell type of transformer. So first we have to draw the circuit diagram. Okay, then the second one, if you see this diagram, it has a single magnetic circuit and it has double magnetic circuit. In core type of transformer, concentric cylindrical types of windings are used. In shell type, sandwich type of windings are used. In core type, core is surrounded by the winding. In shell type, the windings are surrounded by the core. It is easy for repair and maintenance work. It is difficult for repair and maintenance work. Natural cooling is good in core type. Natural cooling is poor in shell type. Core type of transformer is used in the low voltage application. Shell type of transformer is used in high voltage application. Now next is the EMF equation. For derivation of EMF equation, we have to derive E1 is equal to 4.44 phi max F into N1 and E2 is equal to 4.44 phi max F into N2. Now in this derivation, first we have to consider a transformer principle. In that, when we passing AC voltage to the primary side, alternating current flows to the primary and alternating flux is produced. As the nature of the current is sinusoidal, the nature of the flux waveform is also sinusoidal. Hence the waveform of the flux is sinusoidal. Here the flux which is produced in the transformer is maximum flux phi max. N1 is the number of primary turns, N2 is number of secondary turns, F is the frequency, E1 is RMS value of the primary induced EMF, E2 is RMS value of the secondary induced EMF. So by the mutual induction, EMF get induced, and that average EMF per turn, which is equal to average rate of change of flux, which is equal to d phi by dt. Now here we have to find out d phi. D phi is nothing but the change in the flux. So in this diagram, the change in the flux is from 0 to maximum value. So change in the flux is phi max minus 0. dt is the time required to reach flux from 0 to maximum value. Now for this complete waveform, for one cycle, the time period is capital T, which is the reciprocal of frequency. So for flux to reach from 0 to maximum value, the requirement of time is 1 upon 4f. Hence here d phi by dt is equal to phi max upon 1 upon 4f. So average EMF per turn is equal to 4f into phi max. Now in case of purely sinusoidal waveform, form factor is RMS value upon average value, whose value is constant, that is 1.11. So here I am using this relation for converting average value into RMS value. So RMS value of induced EMF per turn is equal to 1.11 into 4f phi max, which is equal to 4.44 f into phi max. Now here we are having n1 number of turns. So E1 is equal to 4.44 f phi max into n1. Same for n2 number of turns, E2 is equal to 4.44 f phi max into n2. So these two are EMF equations of transformer. Now the concept of ideal transformer. In case of ideal transformer, there is a zero leakage flux. That is, the fluxes produced by the primary and secondary currents are confined within the core. That means the flux which is produced in the primary, the whole flux is linked with the secondary. There is no leakage in the flux. Then the winding have no resistances. So there is no drop in the voltages. So whatever induced EMF, they are equal to the applied voltages. Then core has an infinite permeability. So reluctance of the core is 0. Negligible current is required to establish the magnetic flux. Then it has no losses, no hysteresis, no eddy current losses, due to which efficiency of ideal transformer is 100% and regulation is 0. Now transformation ratio. For finding the transformation ratio, we have to consider EMF equations of the transformer, and we are taking ratio of these two equations. So we get the final equation as E2 by E1 is equal to N2 by N1, which is equal to K. Now this K is known as transformation ratio. Now depending upon this K, the transformer is step up, step down, or isolation. So if the condition is number of turns of secondary is greater than number of turns of primary, then the value of K is greater than 1, the transformer is step up transformer. When N2 is less than N1, then K is less than 1, it is step down transformer. When N2 is equal to N1, K equal to 1, the transformer is isolation transformer. Likewise, we have calculated the voltage ratio, that is V1 by V2, current ratio I1 by I2, and turns ratio N1 by N2. Now the relations between all the quantities. Now first we are finding the relation between voltages. So for that I am considering the no load condition on the secondary side. No load condition on the secondary side means the secondary is open circuited. That means the secondary current is equal to 0, and in that case V2 is equal to E2. At the primary side also the current is very small, so the drop V1 and E1 is same. So we get the relation E2 by E1 is equal to N2 by N1 is equal to V2 by V1 is equal to K. Now consider the lossless condition, that means the losses are negligible. In that case, volt ampere, input volt ampere is equal to output volt ampere. So V2 by V1 is equal to I1 by I2. Hence our main final relation is E2 by E1 is equal to N2 by N1, which is equal to V2 by V1, which is equal to I1 by I2, which is equal to K, that is transformation ratio. Now KVA rating of the transformer. KVA rating of the transformer is the output given by transformer at a rated voltage and rated frequency under usual service conditions without exceeding the standard limits of temperature rise. Now the question is why the rating of the transformer is in kVA. Now the rating of the any equipment is depends upon the temperature rise. Now in case of transformer, whenever there is a transfer of electrical energy from primary to secondary, some losses are takes place, and due to that losses there is a temperature rise in the transformer. Now the copper losses, which are depends upon the current, and iron losses, which are depends upon voltage, and it not depends on the power factor of the load. That means the whatever temperature rise, that depends upon the losses, and that losses are depends upon voltage and current. Hence the rating of the transformer is in kVA, volt ampere. Okay, so generally it is expressed in kVA. So kVA rating of transformer is equal to V1 I1 upon 1000, which is equal to V2 I2 upon 1000. Now why this 1000? 1 volt ampere is equal to 1 kVA is equal to 1000 volt ampere. So I am expressing this kVA volt ampere into kVA, hence it is divided by 1000. Now the full load current of primary and full load current of secondary. These currents are the safe maximum values of current which transformer windings can carry. So I1 full load, if I use the relation of kVA rating, that is the formula of kVA rating, then I1 full load is equal to kVA rating into 1000 divided by V1. Similarly, I2 full load is equal to kVA rating into 1000 divided by V2. Now the numericals which is based on these formulas. So consider this numerical. A single phase transformer has 400 primary and 1000 secondary turns. The net cross-sectional area of a core is 60 cm square. If the primary connected to 50 Hz at 520 volt, calculate peak value of flux density, voltage induced in the secondary. So first I am telling you about given data. So here N1 is nothing but the number of turns of primary 400, then number of turns of secondary 1000, area of cross section 60 cm square. Here I am converting it to meter, hence it is 60 into 10 raised to minus 4. This is 10 raised to minus 4. And the primary side voltage is given 520, which is nothing but E1. We have to find out peak value of flux density. Peak value of flux density means maximum flux density. B max we have to calculate. And voltage induced in the secondary means E2 we have to calculate. Okay. So for finding flux density, we have a formula, that is flux per unit area is the flux density, that which is equal to phi max upon area. But phi max is not given, so we have to use the EMF equation of transformer. E1 is equal to 4.44 F phi max into N2. Now E1 is given, frequency is given, and N2 is given. Hence phi max is equal to E1 upon 4.44 F into N2. And the value of phi max, which is 0.005855, we are getting, and divided by the area of cross section So the value of flux density is 0.97 Tesla. Now for finding voltage induced in the secondary, we have to use the relation E2 by E1 is equal to N2 by N1. So E2 is equal to E1 into N2 divided by N1. So answer is 1300 volt. Now second type of numerical, an 80 kVA 3200/400 volt 50 hertz single phase transformer has 111 turns on the secondary. Calculate number of turns on primary, secondary full load current, cross sectional area of the core if the maximum flux density is 1.2 Tesla. So in this case the kVA rating is given 80. Primary side voltage E1 is equal to 3200 volt, E2 is equal to 400 volt, frequency is 50 hertz, and N2 is 111. Now here we have to use the relation, that is K is equal to V2 by V1 is equal to N2 by N1 is equal to E2 by E1 is equal to I1 by I2. So N2 by N1 is equal to E2 by E1. So we are getting the value of N1 is equal to 888. Next, what we have to find out, secondary full load current. Now for full load current, the formula is kVA rating into 1000 divided by V2. Okay, all of you know this formula. I1 is equal to kVA rating into 1000 divided by V1. Here the I2 is asked. So what is I2? I2 is equal to kVA into 1000 divided by V2. So 80,000 divided by 400, that is 200 ampere. And next what we have to find out? We have to find out EMF induced in the primary side. That is E1 is equal to 4.44 F. Now here instead of phi max I am writing here B max into area, because we have to find out area of cross section into N1. So the area of cross section of the core is 135 centimeter square. Thank you.